Okay, so let's begin with a quick recap. Okay, so we are looking at the decoding of, let's say, an NWC WR regular Ldpc code. Okay, so once again, when I say Ldpc code, clearly it's not, this does not define a single code. So what I mean is, I am thinking of a randomly generated, so to speak, parity check matrix H with WC WR regularity, right, and n columns. Okay, so I am going to do this in some way, and then after that I am going to do a decoding for the code with parity check matrix H. Okay, so clearly it is not unique, but let us say we randomly pick one from this set. Okay, and then what is the channel I am looking at? I am looking at okay, so we spoke very briefly about this encoder. Essentially what I said was, you have to convert H to some kind of a systematic form and then do the encoding. Okay, so that's what we are going to do, and that's not very complex because H is sparse. Okay, and then let's say this goes through a BSC with transition probability P, and you get a received vector R. We looked at Gallagher A decoding algorithm to come up with a CCAP. Okay, and this can be this Gallagher A decoding algorithm can be very nicely described in the using the Tanner graph of representation for the parity check matrix. That essentially it's iterative. Okay, iterative, and in each iteration there are two steps. Iterative message passing algorithm. Okay, so that's the main idea. Okay, there are two types of messages that are passed: a message from bit nodes to check nodes, and then messages from check nodes to bit nodes. So there are two parts or two steps inside each iteration. The first step is basically looks something like that. Okay, so particular, the bit to check messages were called V or U? V, right? V? Okay. So these messages VL basically depend on U2 L minus 1 all the way down to UWC L minus 1. If all these guys agree and they are equal to B, then this is going to be equal to B. Okay, else whatever that was received by the from the channel. So what will happen in the first iteration is, you do not have any of these things. Okay, so clearly VL will be set to RI itself. Okay, so that's what happens in the first iteration. All the messages will be equal to RI in the first iteration. In the other iterations, it will depend on the U that is received. Okay, what happens on the check node side is a little bit simpler to describe. What's sent back here, U L minus 1 is simply V2, so UL maybe, right, simply V2L plus V3L plus so on till VWRL. Okay, so these are the incoming messages in the Lth iteration. Okay, so these are the two steps. The messages are basically estimates of the messages. First of all, flow along the edges, and the edges connect a bit node to a check node. Every message is an estimate of that bit node which is connected to that edge. Okay, so that's the main idea. And the next idea that's kind of inbuilt here in these iterations is, if you receive some message from a node, when you send back another message to that same node, you do not use that information. Okay. So, on whatever information is received from that node is not used. For instance, U1 L minus 1 is not used in VL. Okay. So, same way here V1 L is not used in generating UL. Okay. So, you do not use that same information. So, so basically messages have to be extrinsic, that is the idea. Messages are estimates, but they should be extrinsic estimates for that are being sent. It cannot be intrinsic, or it cannot extrinsic in the sense that it should not be previously known to that node that it came from. Okay. So, these are the two rules, and the critical thing that is done. For first thing you can do is first of all simulate this and see what happens. I showed you a plot. Okay. So, and you see that it does well. The next thing is to do some analysis, and for analysis, like I said, like I have been always saying, we will do approximate asymptotic kind of analysis, and the main idea there is this density evolution. Okay. So, what is density evolution? Okay. So, it is basically in density evolution you will track the probability distribution of messages. This is the general definition of density evolution. Density evolution is some algorithm or process which tracks the probability distribution of messages. Okay. So, messages, okay, of course in an iterative message passing decoder. If you do not have an iterative message passing decoder, you do not have any messages to track, that is no problem. Okay. So, first of all, I have been in the previous picture when I described the algorithm, I gave a very simple description with respect to 1 bit node. Of course, in the Tanner graph you have n bit nodes and n times WC edges. So, each edge is now carrying a message. Okay. The first question you should ask is, which messages probability distribution is being tracked here? Okay. Clearly, I mean, if you want to track the probability distribution of every single message, you are not going to be able to do it. Okay. You have to hope or assume that all of them are according to some same distribution. Okay. So, you need some simplifying assumption like that, so that you can track one density as opposed to some n times WC densities, which are impossible to do. Okay. So, that is the first assumption that you need, and for that you need this all 0 code word situation. Okay. Right. Once you assume that the all 0 code word is transmitted, all the RIs have the same distribution, right. Once you make the all 0 code word assumption, what is the distribution of RI? RI equals 0 with probability 1 minus p, and it is 1 with probability p, and it is IID, right, identically distributed for all I. Okay, R1, R2, everything has the same distribution. So, clearly the first message that is going from the bit node to check nodes, you can just think of the message on any edge, it will have the same distribution. So, it is enough if you track that. Okay. Now, as it turns out, I mean, if you make some further assumptions, you can assume the following. You need to basically assume in any situation like this, okay, in any situation like this, the U2 L minus 1 through UWC L minus 1, or in fact U1 L minus 1 through UWC L minus 1 are also all IID. Okay. So, basically the assumption that you need is, okay, so this is okay for the first message. Okay. For even subsequent iterations, you need to assume that all UL and VL have IID distributions. Okay, what do I mean by all VL and UL? Okay, UL represents the message that flows from the check node to the bit node, that is happening on all edges. So, that is what I mean by all. Okay, so, if you look at all these ULs, you have to kind of assume that they are identical and independently distributed. Same thing for VL, the messages that are flowing from left to right, once again we will assume they are all identical and independent. Okay. So, once you make these assumptions, then the analysis is much easier. But what do you need further for these assumptions? All 0 is not the only thing that is needed. In fact, you need some further assumptions for this. Okay. So, I will tell you what you need for that later. Okay. So, you need some neighborhood assumptions, we will see this later, but for now we will assume this and proceed with the analysis and see what we get. Okay. Some neighborhood assumptions are needed, we will see this later, okay, in a little while. But if you assume that this is true, then you can do density evolution relatively in a pain free manner. Okay. So, what is the equation? There were two equations, if I remember right. First equation was okay. So, there are two things we track. The first thing we track is something that I call PL, which is probability that UL equals 1. UL was Q, is it? I do not know. So, one of these things. Okay. So, maybe this was QL. Okay. And then the other probability is PL, which is probability that VL equal to 1. Okay. So, these are the two probabilities that we wanted to track, and we can come up with two recursions. The first recursion is for what I wrote down, I think is for PL. This requires some thought, but I did not really derive it fully, but I assume if enough of you went back and thought about it, you would have found the answer why that is true. Okay. So, you can show this recursion is true. QL minus 1 raised to the power WC minus 1 plus P times 1 minus Q L minus 1 raised to the power WC minus 1. Okay. So, when can VL be 1? Okay, VL can be 1 if Ri was received correctly, received as 0, and then all the ULs agreed to be equal to 1. Okay, that is QL minus 1 raised to the power WC minus 1. Okay. Or Ri was received in error and all the QLs did not agree to be 0. Okay. So, that is the logic for this formula, and you get this, it works out. You can, there are multiple ways of deriving this, but eventually this is the idea. Okay. And then the other recursion for QL in terms of PL is not too bad. That would be something like this: 1 minus 2 PL raised to the power WR minus 1 divided by 2. Okay. So, this is the classic XOR formula. Okay. So, that happens at the check node. Okay. So, this is the 1 minus the odd number of errors in WR minus 1 Bernoulli random variables. Okay. So, that is the idea in this right. And if you have WR minus 1 Bernoulli binary random variables with probability PL of being equal to 1, what is the probability that you will get an odd number of 1s? You do that formula, you will get this. Okay. So, if you substitute Q L minus 1 into this equation, okay, so use this here with L minus 1, you will get a formula of this form: PL equals some function which depends on WC and WR, right. It is parameterized by WC and WR of P and P L minus 1. Okay. You can write down this function, it is not a very complicated function, but it is just that there are so many terms and you have to write it out, and I am being lazy here and not writing that expression out. Okay. So, it is easy to write that expression out, and this is the density evolution formula, DE formula for Gallagher A over BSC P. Okay. Right. So, of course, in any iterative formula like this, you need a starting point. Okay. What is that starting point? P0. What is P0? Okay, I think it is good to think of P1, right. So, we are numbering iterations from 1 onwards. So, what is P1? Probability that VL equals 1, V1 equals 1. What is V1 first of all? V1 is simply Ri, right? What is the probability that Ri is 1? P. Okay, so it is equal to P. Okay, so that is the starting point. You plug it in and you keep repeating this, you will get the probability that VL equals 1 in the Lth iteration. Is that okay? So, this is the density evolution formula for Gallagher A decoding algorithm over BSC for the WCWR regular Ldpc codes. Okay. So anyway, so there are numerous things to notice in this formula. So, one of the let's see what is missing. Okay. So, what is missing in this formula? What do you think should be there in the performance of a code or probability of error analysis of a code? N is clearly missing, right. So, that's something that is clearly not correct. Of course, this formula cannot be exact. If you have a finite block length n, this n has to show up somewhere. I mean, you can't just have probability of error independent of n. You remember in ML probability n clearly shows up, right. So, obviously n will show up somewhere and n is not showing up here. The reason why n is not showing up here is this formula is valid only when n is infinite. Okay. If n is for any finite n, this formula will not be valid. Okay. Eventually there will be an L, maybe for L equals 1 it will be valid, but eventually there will be an L for which this formula will not be valid for any finite n. If n is very large, you can make it be valid for any large L. Okay. So, that's definitely true, but the crucial thing to understand is this part. Okay. Right. The all zero code word played a very enabling role, as in we could just reduce the number of messages whose probability distributions we have to track just becomes 1, it is just one random variable you have to track. All the messages are IID in the first iteration itself because of the all zero code word. If you did not have the all zero code word assumption, then you can't do it, right. You can't track it very easily. So, some errors will be messages being 0 will be an error. For some errors, message has to be 1. Okay, and you can't track those things very easily. So, you just get totally lost. Okay. So, all zero code word assumption can be justified without too much trouble for the BSC and the Gallagher A decoding algorithm. You need a certain property called symmetry for that, and we do not have too much time in this course to discuss that, but let us just say it is okay. But the other problem which is more interesting from a code construction point of view is this neighborhood assumption. Okay. So, this will help you in actually generating a parity check matrix, okay, a good parity check matrix, so to speak, from the ensemble. So, that is why we should spend some time in understanding this. So, what do I mean by saying all the VULs and VLs should have IID distributions? Under what conditions on the neighborhoods that is on the graph or on the Tanner graph is this assumption valid? That is the first question we will ask, and we will try to answer that next. Okay. So, anyway, we will come back and look at this formula much more closely, but I want to first settle this neighborhood assumption once for all, and then we will proceed with this formula. Okay. So, let us look at UL. Okay. So, you have a particular, let us look at VL, you have a particular bit node, okay, and then there is an edge that is connected to this. I am drawing it kind of in the upward direction. So, maybe you can just to make the thing a little bit more clearer. Okay. So, let us say this is some VL. Okay. So, the question I want to ask is, how was this computed? Okay, maybe there is a check node here obviously. How was VL computed? Okay. Okay, it was obviously computed using UL minus 1s. Okay, and where did I get UL minus 1s? From, let us say we just use, let us say WC equals 3 and WR equals 4 for this picture. Okay, you can do for anything else also, but the picture will just become more messy. So, I will just use it for these small values. I can make a nicer picture there. So, how many other will be there? 2 other check nodes will be there, and you would have got U, say U1 L minus 1 and a U2 L minus 1 from here. Okay. And then if I have to answer this question completely, I have to somehow make my way all the way down to the RIs, right, because RIs is what you got from the channel. Eventually, when you did all the iterations, VL will ultimately be some function of the entire vector R, it can't be something else, right. So, when I say ask this question, how was VL computed? How was VL computed using R? That is the question I am asking. Okay, VL definitely is a function of R. What is that function explicitly? Suppose you have to specify that. How will you go about doing that? So, it turns out you have to kind of unwrap your Tanner graph. Okay, so this is the unwrapping that I am doing. So, you start with this particular edge, and VL was going on that particular edge, it was generated using the 2 ULs. How were these ULs generated? From V L minus 2, right. So, and where did the V L minus 2 come from? Or V L minus 1 maybe, yeah. So, V L minus 1, where did that come from? From 3 other bit nodes, and once again here the V L minus 1 would have come from 3 other bit nodes, okay. And then what will be the next question I ask? This is V L minus 1, how were the V L minus 1s computed? That would have been computed from U L minus 2, okay, and that would have come from 2 check nodes. Okay. So, this is U L minus 2, and then you will have a V L minus 2 and so on till you get all the way down to just bit nodes which are just V 1, okay, and that is equal to R. Okay. So, V 1 is the last thing you have, and that will have a whole bunch of bit nodes. Is that okay? And that will be just R, R1, R2, whatever, Ri's. Okay, so let me just write down Ri because I do not know which coefficient will be there. So, these are all Ri's. Okay. So, such a tree is called a computation tree. You can call it a computation tree if you want, you can call it a neighborhood. Okay. So, there are several properties for this tree. You can say a lot of things about how many nodes that there will be at each level, okay, each depth, so to speak. Okay. For depth 1, depth 2, etc., you can keep on in terms of WR and WC, you can answer that question. But what is important is for any edge I pick from the bit node to the check node, this tree will have the same structure for regular codes. Okay. As long as the code is regular, for any edge I pick, it will have the same structure. Okay. Same structure, same kind of unfolding will happen. But so the next thing to keep in mind is, okay, so that is fine, the same structure is fine, but what about the actual nodes that show up there, show up all the way here, okay, will they all be distinct? That is the next question that you have to ask, which is very important, okay. But will all the nodes be distinct? This is quite important. Why do you first of all want all the nodes to be distinct? Okay. So, there are a lot of intuitive reasons why all the nodes will have to be distinct, but a very statistical reason is that if all the nodes are distinct, then what happens? My independence assumption is true, okay, right. If all the nodes in this computation tree are distinct, okay, then my formula for VL holds exactly, the density evolution formula for VL holds exactly. Okay. So, PL, that is probability that VL equals 1 will be exactly that probability. That happens only when all these nodes are distinct, because there is no dependence. See, all the Ri's are independent here, and the way I am combining them, as long as all these nodes are distinct, they will all come from independent observations, and if at every step independence is satisfied and my formula for PL is valid. Okay. So, if this is true, this implies, this is true, PL is actually the probability that VL equals 1. Okay. So, those are the 2 points that I want you to observe and keep in mind. For regular codes, the structure of this unfolding in this computation tree or the neighborhood of the particular edge remains the same for all edges, okay. And for a particular level L, for a particular iteration L, if this entire computation tree has no repetitions in any node, no check node repeats, no bit node repeats, if that is the situation, then the density evolution formula for PL is exact. PL is the probability that VL equals 1, and that is exact if you have the all 0 code word and you receive Ri corresponding to that. Okay. Is that, hopefully that is convincing. It is not a very difficult argument. I did not write down the full proof, but you can see how it works. I mean, it is all independent, everything is working out very nicely. Okay. Is that clear? Everybody is happy? Okay. So, now you have to ask the question, how can I construct a hedge so that this is satisfied, not just for one edge, but for every single edge. Okay. So, that is the question you should ask from a construction point of view, because if you were to construct for let us say L equals 10, okay, so let us say 10 iterations you want to do, and you want the 10 iterations to be accurate and your density evolution formula to exactly reflect what happens, then what should have happened? In every neighborhood computation tree that I did for every edge up to depth 10, okay, so depth is like iteration 10, what should you get? What should you not get? You should not get any repetitions in the nodes. If you constructed your original graph in that fashion, then you can be guaranteed that your density evolution analysis will work. Okay, otherwise there is no guarantee that it will work. Okay. So, now that this seems like a bit of a crazy requirement for a graph. Okay. So, what does it mean in terms of the graph? It turns out you can simplify that requirement. Okay. What happens when any node repeats in this tree? What does it mean from a graph point of view? Is there anything you can make? Suppose this is check node repeats here. What does it mean? You have a loop in your graph. Okay. So, if this check node repeats here, it means this guy becomes a loop in your graph, loop or cycle. Okay. Cycle is a much more standard term. Okay. Right. So, if I want my computation tree for iteration L to be free of any node repetitions, okay, what type of cycles should not be there in the graph? Okay. So, no cycle of length less than 2L it will turn out should not be there, no cycle should be there. Okay. So, cycles of length less than 2L should not be there in the Tanner graph. If you can guarantee that in your construction that there are no cycles or loops of length 2 times L. Why did I say 2 times L? Yeah. So, just look at this graph will have a total depth of 2L. Okay. It is not L, right, because L minus 1 is appearing twice. So, you see everything will appear twice. So, it will have a length of 2L. Okay. So, if you can avoid all cycles of length less than or equal to 2L, okay, yeah, that is the thing, no cycles of length less than or equal to 2L must be there in your Tanner graph. If that condition is satisfied, then you can do L iterations, okay, with the density evolution formula accurately reflecting the probability of bit error. Okay, remember probability of message error. Okay, that is the key idea here. Okay. So, let me summarize that, write it down. Okay. No cycles of length less than or equal to 2L in Tanner graph implies okay, L iterations follow DE formula. Okay. That is the basic idea. So, in a way you are not doing anything wrong in the decoding, everything you have done up to that point L iterations is as it should be, you are not making any approximations or mistakes. Okay. Is that okay? So, the length of a minimum cycle in a graph is called girth. Okay. So, girth is a technical term, length of shortest cycle, let me say shortest cycle in a graph. Remember, in a bipartite graph you can only have even length cycles, you cannot have odd length cycles, because if it has to come back, right, it has to go there and then come back again anyway. So, for a loop you will have even number of length, even length. Okay. And if you have in the socket construction, girth 2 is possible, right, because you can have multiple edges from between 1 bit node and 1 check node. In the socket construction, girth 2 is possible, but if you avoid multiple edges, clearly the minimum girth possible is 4. Okay. So, if you have girth 4, then how many iterations can you do? You can do 2 iterations.
Oh, one.
Yeah, 2 you cannot do, right?
1.
So you can do only 1. Is that correct? That also is not correct actually. So I think there's some 2l minus 1 that I'm missing here. If you have girth 4, it turns out there's an overlap of 2, so you can't even do 2 iterations. So maybe there is like a 2l minus 1, no? Okay. So I guess that's 2l minus 2 I have to look at, right? Maybe let me make sure if I have, let me see if I have any nice expressions written here. So I don't seem to have it, but I think this should be like 2l minus 2 maybe. Okay, because this length, this depth is what? 2l minus 1, right? Okay. Yeah, so it has to be 2l minus 1. Okay, so you should not have 2l minus 2. Is that correct, or is it 2l plus 2? Okay, so let me think about this carefully. I'm getting a little bit confused here because I'm not sure that if I recall correctly, if you have girth 4 or if you have a cycle of length 4, you should not be able to do even one iteration, I think, because even that one iteration will cause some trouble, because you will have structure like that. I'm sorry, you can do one iteration, is it? Okay. Oh, okay. Oh, there will be a problem. So I guess 2l was okay, I guess, right? 2l is okay. Okay, so I guess you can do one iteration if you have girth 4. Yeah, the one iteration is maybe not too bad. Only when you combine it and send it back, you will have a violation of your probability density evolution formula. You are right. So P1 of course will be correct, it's just Ri, and then Q1 will also be correct. Okay, only P2 will be wrong. Okay, so yeah, you are right. So this is fine. This is fine. I think 2l holds. Okay, so if you have girth 2, you can do one iteration. Girth 4, you can do one iteration. You can't do more than that. If you have girth 6, then you can do 2 iterations. Okay, so even to do the second iteration, when I say can do, I mean you can up to 2 iterations, the density evolution formula will continue to hold for probability of error. That's what it means. Okay, not that, I mean you can do any number of iterations. Nobody is stopping you from doing the iterations, but density evolution formula may not hold. That's all. Okay, so in typical constructions, okay, so this is in practice. In practice, what you do is when you construct, you avoid length 4 cycles. That is, usually for most graphs that you use, girth will be 4, girth will be 6, I am sorry, so what am I saying, girth will be 6. Okay. So there are some graphs that have girth 8 maybe, okay, so but this is a bit more rare. Okay. 6 is very common for most lengths, and 6 can be easily ensured. You can write a very small simple program to make sure that there are no length 4 cycles. You can construct it very easily, it works quite easily, but beyond girth 6 it is very difficult. Okay. So if you for instance say if you want to construct a 1000, 3, 6 code, usually you will get girth 6. Okay. It is difficult to go beyond girth 6, maybe girth 8 you can do, maybe 10 maybe, but beyond 10 and all you can't do much. Okay. So you can't construct, it just takes so long, and maybe they don't even exist, I don't know. Okay. So it's difficult to construct these kind of things. So usually people settle for girth 6. Okay. So it turns out in practice, even though the density evolution formula does not hold, okay, the decoder works relatively okay, it doesn't become very bad. For instance, in the plot that I showed you yesterday, I showed you some plots. The graphs that I constructed have only girth 6, don't have girth 8 or anything, only girth 6, and still you could see that the bit error rate was falling quite steeply. Okay, as I increase block length, it was falling steeply. Okay, so what do we make of the density evolution formula then? Okay, so that's a question you have to ask. Okay, so basically it means that it is a good formula even if the assumptions don't hold. Okay, so as long as if you remember, the threshold was computed using the density evolution formula. So density evolution formula is good even if the independence assumption does not hold. Okay, so you have to take that with a pinch of salt. It's not accurate anymore, but it's approximate, but it works. Okay, is that okay? So it's like saying I have a sine wave. You can never have a sine wave forever. You say always say you have a sine wave, right, because it is very useful in practice and it is a great approximation, all your problems work out great with that. So, you think of the sine wave. So, likewise we will think of density evolution in similar fashion. Okay. It is an approximation, but it works very well in practice, okay. Or maybe the delta function, okay, that is another nice thing to remind yourself. I am sorry. Okay, so I will come to that, 1 minute. So, but what you can show is the following, okay. So, in the socket ensemble, okay, you can show some interesting results using counting and some very clever probability arguments, okay, maybe even more advanced probability arguments. You can show that the probability of a cycle in a depth, let us say a depth 2L neighborhood okay, this is less than some constant that does not depend on n obviously divided by n. Okay, so you can show this. Okay, so this of course involves some interesting arguments. There are various ways of showing it. Okay, you can. It's not too bad. The argument is not very bad. I'm just not providing it here. Okay, so it's quite easy in not just the socket ensemble, even in other ensembles you can show this. Okay, so if you fix one particular edge and then look at its depth 2L neighborhood, what's the probability that you will have a repetition? Okay, what's the probability that you will have a cycle is less than some constant divided by n. So what does that mean? As n becomes very large, this probability is going to tend to 0. Okay, so you won't have a cycle with high probability. All right. Okay, so that's a good thing. But what's not a very good thing about this formula? It would have been nice to have something larger than n. Why would you have something larger than n in the denominator? Because the number of such edges is what? You have n times WC edges and you want all the neighborhoods to have very low probability. The probability that all the neighborhoods have a cycle should go to 0. Okay, but this thing does not quite guarantee that. Why? Because when you multiply by n, if you want to use a union bound and multiply by n, you get a constant. Okay, and that constant many cases will be greater than 1, which means you don't get any information from this inequality for all the neighborhoods. Okay, in fact you can show that won't happen. So you need more nuanced analysis to show more interesting results, but this is interesting nevertheless. Okay, so every neighborhood with high probability will not have cycles, but when you look at all of them together, you are pretty much guaranteed to have cycles. That's why I said girth 6 and all is unavoidable in these constructions. You will end up getting some girth. Okay, that's the idea. All right, if you haven't studied all of these asymptotics and probability, what will not make sense to you at this point is every neighborhood has very low probability of not having a cycle, but why is it that all neighborhoods together have a very good probability of having a cycle? Okay, so those are things that work because of this n. I mean it's going to it's not really that low. That's what it means. It's only constant by n. It's not constant by n squared or n power 3. Okay, so it's not that low. It's not low enough. Only if it is very low, you can be sure about all these other things. Okay, this is why I said this formula is valid asymptotically. Okay, so another type of analysis which is again equally interesting is to fix n and let L go to infinity. Okay, right? Then you can't use density evolution obviously, right? So you have to do something else, and that also is possible. People have done some work in that direction also. So there's lots of work in this area. Like I said, it's matured very fast. People in the last 15 years or so have worked a lot on this, and a very good reference for all this is modern coding theory. This book, Modern Coding Theory, by Urbanke and Richardson. It's a tough book to read, I'll warn you. if you do not have a lot of what is called mathematical maturity, it is a particularly more difficult book to read. Okay, so it has a lot of technical details, and you have to have some comfort with reading technical literature. Okay, so if you can do that, then this is a good book to read. Okay, it has all this information, but otherwise the information is in papers. Papers are more difficult to read than textbooks. So maybe this is a good thing to read. Okay, so where are we now? So we have this density evolution formula. Where is that? Here is the density evolution formula, and we have a reasonable idea of when this formula is valid. Okay, so it's valid when what? Okay, there are two things that you have to keep in mind. In theory, when is it valid, and in practice, when is it valid? In theory, it's valid when, well, not really anywhere. Okay, anytime, not for, only for one particular bit, or so to speak. I mean, just one edge it's valid. Okay, not for all edges together. Okay, you can't take it like that. Okay, it's not valid in that case. Okay, even asymptotically, it's not valid if you take all edges together. Okay, but in practice, it seems to be a very good formula. Okay, so it predicts the behavior for large n very accurately. Okay, so that's the way to think about this. Okay, any question? I think all this must be totally new to you, but nobody seems to be disturbed by it. Maybe you have studied enough things like this, or it's any questions, any comments?
So the cyclic nature talks about dependence of VL with the same V of some other iteration. I am not able to get how it.
The same V. Okay. Hey, I just drew the. I wrote down everything as V, but it's not V really. You know, I mean, each edge is different. So.
Okay.
You have to think about it differently. So if there is a repetition, some edges will also repeat. Okay. So other than that, that's why I put U1, U2 here, but then I can't put V3, V4. I mean, it just becomes messy. It's difficult to write down. Okay. All right. So now let's given all these conditions under which the density evolution formula is valid, let's look at that formula more closely and see what we can say about it. Okay. So that's what we're going to do. The formula we have is of this form: PL equals F WR WC P PL minus 1. Okay. So this is the form that we have. All right. Is there a question, Sagar? No? All right. So what you do for this is you fix P, WR and WC. Okay, and okay, of course WR and WC you always fix, so let me not say that. Okay, WR and WC are fixed. Okay, so you fix the WR and WC. Okay, and then first thing you can ask is, you fix P, and this function simply becomes a function of one variable PL minus 1. Okay, and you can do some very basic calculus to analyze that. For instance, you differentiate it and figure out if it's positive or negative, and you can show that this will be a monotonically, what can you expect as a function of PL minus 1, this function will be a monotonically decreasing, right. So it will be monotonically decreasing. Okay, so you fix P, F WR WC is monotonically decreasing in PL minus 1. Okay, these are analytical properties that you can show. Okay, and the other thing also is to fix P L minus 1, and then again you can show this is monotonically decreasing in P. Okay, is that okay? All right. So what's interesting is, what's interesting now is, you can ask an asymptotic question. You fix P, okay, and ask the question, what is P infinity? Okay, P1 is equal to P itself, and P2 is going to be something lesser than or equal to P. Okay, and then P3 will be lesser than or equal to the previous thing, etc., etc. So that's going to be definitely true, but the only thing that can happen now is P infinity might either be 0 or some positive value less than or equal to p, okay, some non-zero value or 0. Okay, so that's the question that you ask. So what you define as the threshold is the following: p star is actually, so you look at all those p's such that p infinity is equal to 0. Okay, so I am saying equal to, so obviously there is no equal to here, this is all limits. Okay, so the way I should write this down actually is limit as L tending to infinity of PL. Okay, so that's how I should write it, simply writing it as P infinity equal to 0. So that limit, this is P infinity. Okay, so this clearly is a function only of P, right? For a fixed P, you will get a P infinity, which might either be 0 or not. Okay, so I am going to look at this set of all P such that P infinity is equal to 0. For instance, P equal to 0 is clearly an entry in this set, right? P is 0, then P infinity will clearly be 0. It's nothing more that can happen. Okay, no error at all. So as you do iterations, you are not going to introduce new errors. Okay, well you are not going to make that situation worse. Let me say that. Okay, and as you slowly increase P, you will still get P infinity going to 0 for a while. It turns out you can show those things. You can show those properties for this iteration. Okay, and in this set, okay, so usually this is a set of real numbers, and it will be an open set. Okay, and you can't define what's called a maximum in an open set. Okay, so what's the right word to use? You have to use supremum. So I am going to say supremum. If you don't understand supremum, just take it as maximum. Okay. Anyway, well, all these open sets don't exist, right? What you can compute with is only rational numbers, and those things not even rational, finite precision numbers. And finite precision numbers, clearly there will be a maximum. So think of it as maximum of P such that P infinity goes to 0. Okay, so that is called the threshold for this iteration, and you can show such a threshold will exist. Okay, so there are analytical ways of showing that the thresholds exist. Okay, so it's not just a vacuous definition, it does exist and you can compute it. Okay, you can definitely compute it. How do you compute this? Yeah, just you can, as in numerically you can easily compute it, right? Okay, you write a MATLAB program, you try a small p, like then see what happens to P infinity, then you increase P by some finite precision, not finite precision, but finite precision you can definitely compute it numerically, there is no problem. Okay, see when it does that. So this is again a very interesting MATLAB program to write. Okay, so it's a very simple program, it's a few lines of MATLAB code, you can very easily write it. And if you do that for WC equal to 3 and WR equal to 6, you will get P star to be around 0.04. Okay, so let me see if all that I told you about the density evolution has sunk in. Okay, so what does it mean if P star is 0.04?
So we'll be able to identify what your code word was.
So you are saying roughly correct things which will be okay in practice, but really theoretically it does not mean much, I mean it just means that the density evolution formula is going to change its behavior at this P star. Okay, and for each bit, for each edge, the message that is going to go through that edge will be in error with probability tending to 0 for P less than P star and P greater than P star. But as a total, when you decode, what should happen, the density evolution formula does not predict, because it is not valid in those cases. Okay, but in practice we saw from the plot that as n increases, the bit error rate is clearly falling very close to 0.04. Okay, so what you expect in practice is the following, and that is captured very nicely by this P star. Okay, so maybe you can't theoretically prove it in a very sound way, but what will happen if you plot BER versus P is, there will be this P star, and as you keep increasing n, what will happen? Something like this will happen. Okay, you are increasing n for the same 3 comma 6. This is the picture that I showed you last time also. This is just a rough version hand version without any access etc., but I showed you the actual picture at that time also. Okay, in last class I showed you the actual picture. This is what you expect to happen, okay, which is true. Okay, but what it means theoretically, you need to really read a lot and really figure out what it means theoretically. Okay, but it is a good analytical tool and it gives you a very nice picture in practice, and that is true. All right. So, to make a full complete theoretical statement, you need to go into the cycles and what happens with that probability, and so what is this, what is that, etc. So, you may not be able to make a very complete and concise theoretical statement, but in practice this is eminently true. Okay. So, this is what you expect. So one nice thing that happens because of this is you do not have to do all these simulations to answer some design questions. Okay. So, for instance, one design question you might ask is, if I want my design rate to be half, okay, I will show you the utility of threshold. It is very nice to have it around. If I want my design rate to be half, I can pick WC equals 3 and WR equals 6, or I could pick WC equal to 4 and WR equals 8, and so on. You can keep doing that, right. So, which one is better? Should I stop somewhere or should I keep doing it? Which one is the best? How do you answer that question? So, one nice way to answer that is you compute P star here. So, this works out to be 0.04. This P star, if it is greater than 0.04, then this is a better thing. Okay. If it is lesser than 0.04, then you might as well settle for 3 comma 6, etc. Okay. So, this is how you use the threshold to answer design questions. Okay.
So, you said mortality decreasing, let's say the rate of decrease. So, how can you say that maybe for a finite number of iterations one code may, I mean,
we don't even know if it's regressing here.
Okay. So,
better than the first.
yeah, so maybe you have to analyze that, but it will work out the same way. I think if P star is lesser, you will see even for finite number of iterations it will be the same way. Okay.
More chances of number of iterations being independent is reduced.
Well, it all depends on n. So
Yeah,
For the same n.
for a fixed n, okay, yeah. So I guess it all comes down to this kind of a plot. I mean, so what you do is you make a plot like this, and definitely you compare, you will get your answer. But P star is a good starting point. I mean, if it's lower, then it's very likely to be, if P star for this is higher, then this is likely to be a better code. And you'll see when you actually simulate it, as long as you take care to avoid girth 4. Girth 4 for some reason is bad. As long as you have girth 6, it's okay. Density evolution formula, at least for bit error rates of 10 power minus 6, minus 7, minus 8, maybe even minus 9, it's okay. Maybe if you go below that, they'll see something, but 10 power minus 9 is so low that in many wireless applications, at least nobody looks at such low BERs. 10 power minus 5 is good enough, right. So if you want only 10 power minus 5, you go to block length of thousands or 10,000s, and then you compare these things, you will see the density evolution formula is really good. I mean, it's not bad. Even iteration after iteration, you will see it captures the bit error rate very nicely. Okay, so it's not bad. Okay, so one thing I should quickly point out. Remember, PL is probability that VL is in error or is in 1. It's 1. It's not the same as bit error rate, right. It's only message error rate in your message passing decoder. How will you go from this to bit error rate? Yeah, so you have to use the final decision making logic. What was my final decision making logic? It did not involve VL at all. It involved QL, because it involved only the use, right. So you have to look at the bit node, all the messages it receives, all the use and the RIs. I'm going to take a majority decision kind of thing, right. So that's my final decision, right. So it involves QL and then the P itself, okay. But of course, if PL tends to 0, QL will also tend to 0. Okay, so everything is okay. It works out quite nicely. So, but this is a formula that you have to use. I mean, you can't just directly say PL is okay. Bit error rate will be some function of QL. Okay, so this will be some function of P n QL, QL minus 1 maybe, okay, right. So, you remember what do we do? So, you have WR messages that are coming from here, right, U1, U2, UWR, and then you have RI itself. What is my decision? Some kind of majority of these things, okay. So, that is what will determine this function, okay. So, it is a bit more complicated than just PL itself, okay. So, if you compute bit error rate using this, it is pretty good. I mean, for large n, when I say large n like 10,000 and all, it is a very good formula, okay. So, this utility as a design tool, it is very vital, okay, for threshold. This is the major selling point for threshold, okay. You can design what is known as degree distribution, okay. So, what is the degree distribution of your Tanner graph? What are the left degrees, what are the right degrees, right. So far we are looking at just regular, so there is really nothing much to describe, but even here threshold is a very useful measure for a particular rate. You look at a particular rate and decide which is the best code that you want to do, okay. And then after that you have to construct a parity check matrix. For that you have to use girth criteria, okay. So, you have to try to maximize your girth. It is a bit more complicated, but you can write that, and then you run Gallagher, you will get your answer, okay. So, once again all these are good programs to write. If you have the time, then you should write a program for computing the threshold for Gallagher given WR and WC, figuring out which one is the best, and then write a program for generating a parity check matrix with these constraints, then write a program for maybe encoding, then you write a program for decoding, then you have the entire simulation ready with you. You can generate these kind of plots, if you have all that, okay. So, okay. So, this is kind of like a point where we are going to make a bit of a deviation. So, in case you have any questions or comments on this, is a good time to ask. Any questions? You're okay? Feel this is good? Okay. So, you see the other problem, right? So, the other problem I was talking about is this problem of coming up with exam questions. Okay. So, you can't come up with any exam question in this area, right? What kind of exam question can I ask? The only question I can ask is write down an algorithm for doing something like this. Nothing else I can ask. It is very difficult to design any good coding question. Of course, you can ask analytical question, calculus questions I can ask, show that this is an increasing function of that, but I am assuming you have seen it somewhere. You would know how to show something is an increasing function, right? So, stuff like that is what can be asked. I mean, you cannot ask a real good coding question. Maybe if I come up with a question, then you will have to answer that. Okay. Okay. So, what we are going to see next is this idea of irregular codes. Okay. So, this is where the threshold really helps out, and here again the notion of the threshold is now will become more approximate, okay. So, you might think when you make it more approximate it may not hold, but it turns out it is a very good tool, okay. So, it ends up being a really good tool for designing codes with finite bit error rate, as in finitely low bit error rate, like 10 power minus 5, 10 power minus 6 and all. If you want to show like asymptotically low bit error rates, like arbitrarily low bit error rates, then you can't do it with threshold, but if you want to show just finite but low bit error rates like 10 power minus 5, minus 6 and all that, you can do by simulation, right. If you want to show 10 power minus 5 bit error rate, you can simulate and show. So, for those things these irregular codes are really good. So, in fact most standards use irregular codes, they do not use regular codes. So, what are irregular Ldpc codes? What are irregular Ldpc codes? Sparse parity check matrix, okay. So, that holds always, but then what? Yeah, number of column and row weight is not constant, okay. Column and row weight, okay. So, but having said that, usually you can't allow all kinds of column weights, I mean, of course the row weight can be anywhere from 0 to n, right, n is the block length, you can't allow every single row weight, and then you can't design it, you can't analyze it, nothing can be done. So usually what is done is there will be something like, let us say, I think most standards do even lesser, but usually let us say 10 or 20 different column weights, okay, and then in fact for row weights it will either be 1 or 2, that is all. That is kind of people have kind of settled down to that. You can think of other options also, I am not saying other options are bad, but usually in practice people use roughly let us say even 5 to maximum 10 different column weights. Remember, these column weights are also what? Are also left degrees, right, in your Tanner graph. If you think of the matrix, then it is column weight, in the Tanner graph it is degree of the left node, which is called left degrees. Usually you use 5 to 10, I am just giving you a figure of rule of thumb here, you can also use 20 if you like, but it just gets more complicated. And for column weight you use either 1 or 2, or row weight, I am sorry, 1 or 2 different row weights or right degrees. Okay. So this is just to simplify this vast set of possibilities. Okay. If you do not put it down to this, then there are too many possibilities, you can't make sense of all of them together. So we must make some simplifying assumptions in restricting our set. Even though it is irregular, it is not that irregular, I mean it is moderately irregular, okay, that is the way to think about it. Of course regular codes are a special case of irregular codes, it has one column weight, one row weight, it becomes irregular. So you can't think of regular codes as being a distinct set from irregular codes. Irregular codes also include regular codes. Okay. All right. So now we need notation, right. Previously we had just n being the block length and WR being the row weight, WC being the column weight. That's it. That was enough. Now obviously that won't be enough. You need more notation, and WC1, WC2. Okay, that's not standard though. I have to use standard notation. So I'm going to introduce all this notation now. It's a bit, it's not very confusing, but still, it's painful. So let's just do this. Okay. So to specify the irregular codes, the distribution. So this kind of a thing is called degree distribution. The number of different degrees, number of different row weights or column weights is called degree distribution. So when you specify an Ldpc code, usually you have to specify the block length n and a degree distribution. Okay. So how do you specify degree distribution is what I am going to talk about now. Okay. So you can do it in two different ways. First thing I will do is what is known as degree distribution from a node perspective. So this is what makes most sense. Okay. What is this degree distribution? It is very simple. L sub I we will say is the fraction of bit nodes of degree I. And what is this I? I is going to be, let us say, usually it starts with 2. Okay, you do not want to have degree 1 bit nodes, but it can also start with 1. Okay, so of course it can start with 1, but usually it starts with 2. Okay, there is a corresponding thing for check nodes, and that is called Ri. Why am I using Li and Ri? Left and right. Good. Okay, so Ri is for check nodes. Okay. So what I am going to do next is going to be slightly, I mean it is just some simple counting, but it is always confusing to people when I do this simple counting. So let me try and do this in as painless a way as possible. Okay. So, suppose I say n is my block length, okay. How many nodes do I have of each degree I? Li times n, right. So, I have Li n is the number of nodes of degree I. Okay, so clearly this has to be an integer. So, your Li is limited in what's it called, in the number of decimal places it can have, or accuracy, or what is it called, resolution. Okay, so you can't have all kinds of Li's, root 2 and all, for instance, is not possible for Li. You can't have, or 1 by root 2 maybe if you want something less than 1. So, you can't have such irrational numbers, okay. But usually such restrictions are not imposed, you just assume Li is something, but then what do? You simply approximate this Lin, you just floor it or seal it and take something which is approximately the same degree distribution, but not the same. Okay. From n. Yeah, it can be that way ultimately, yeah, it has to be something divided by n. So, but usually when they specify it, they specify Li usually to some 10 decimal places or something. So, when you do that, you simply floor or seal this Lin in your design, that is the idea. Okay. Is it okay? So, my question now is a little bit more difficult. How many rows, suppose n is the block length, what is the number of rows in my parity check matrix? Okay, so this requires some little bit more nuanced counting than before. It's the same as last time, but except that now you have the number of ones is a little bit more difficult thing to compute. Is it? Is it more difficult to compute? I don't think so. How do you compute the number of ones?
I times Li.
Okay, number of ones is equal to what? Number of ones in the matrix. See, it has to be summation I times Lin, right, when you count it from the column perspective, and when you count it from the row perspective, it should also be summation j times Rj number of rows. Okay. So, what is going to be the number of rows? So, number of rows equals summation I Li divided by summation j Rj times n. So, what will this reduce to in the regular case? It was simply Wc by Wr. Clearly, when I equals Wc, Lwc is 1. Every other L is 0 for the regular case. So, that works out properly the other case also. So, this is the number of rows. Okay. So, of course, this also has to be an integer, right. So, there are further constraints on these Li and Rj and all that. You can't have arbitrary choices, but once again, if it is not an integer, what do? Usually you adjust these coefficients without too much change to make it an integer. Okay. So, that is the idea usually. Okay. All right. So, now what is design rate? Is 1 minus number of rows by n, and that is 1 minus summation I Li divided by summation j Rj. Okay. So, to write this, make this formula look more sophisticated, so what is usually done is people write it as 1 minus L prime 1 divided by R prime 1 where L of x now is summation Li x power I, okay, and R of x is summation Ri x power, well, Rj x power j if you want. I power x, what is this?
No, x power I.
X power I.
Why did I power x come? It's x power I. Okay, so what is L prime now? What is L prime of x?
Sigma I
summation I Li x power
I
minus 1, and then when you put x equals 1 in L prime, you get summation I Li. Just to make it look a little bit more sophisticated. If you do not like the sigmas, you can do the primes and it looks like this. Okay. So, these are called degree distribution polynomials, okay, and it is a common way of specifying the degree distribution. Okay. Okay, so let me leave you with one final computation which is quite simple again, which is a very simple example. I am going to say I want a design rate of half, okay, and then I am going to say L1 is 0 of course, L2 is half, L4 is 1 by 4 and L7 is 1 by 4 again. Of course, the other Li's are 0. So, what is L of x? X squared by 2 plus x power 4 by 4 plus x power 7 by 4. Remember, summation Li has to be equal to 1, right, because these are all fractions and fractions of bit nodes. So, summation Li has to be equal to 1. Okay. So, I do not know if I mentioned that somewhere, summation Li has to be equal to summation Rj, this has to be equal to 1. Okay, this is also important, keep that in mind. Okay, so this is my L of x, and for the right distribution I am going to say R7 and R8 are not 0. Okay, every other Rj is 0 for other j, and the design rate is half. Okay. Given all this information, let us see if you can spend the next 100 seconds to find out what R7 and R8 have to be. Will you, first of all, will you get a unique solution or will you get multiple solutions? Yeah, you will get a unique solution because there are two equations, right, R7 plus R8 is 1 and then the other equation for the design rate. So, essentially you will get a unique answer. I want you to tell me what that answer will be.
One by 2.
1 by 2. Okay, so that is the correct answer. So, you can show R7 equals R8, R of x equals essentially x power 7 by 2 plus x power 8 by 2. Okay, nobody asked me what this x is. X you accept, you know, alpha is something that disturbs you, x somehow you accept. So, it is just some placeholder variable, it does not mean anything, it is just there so that I can differentiate, okay, nothing more. Alright. So, this is one example. So, this is how it will look. Usually there will be a few degrees, not too many of them, and the fractions will be some nice numbers like this, you can keep them as some nice numbers and you get these irregular codes. Okay, so, we will stop here. And the next thing we will see is how density evolution is extended for the irregular case. Like I said, it will be a little bit more complicated approximation, but we will do that, and then why that is useful for irregular codes, for optimizing irregular codes. So, now you see, if I fix design rate and ask you for the best irregular code, the choices are much more. So, can you get a much better threshold than what you got for the regular case is the question. Okay, so, that is why irregular codes are interesting. Okay, so, you just increase the choice for a given design rate. For a given design rate with regular codes, you had only 3, 6, 4, 8, 5, 10, that is all, nothing more. Okay. For irregular codes, now you have so many possibilities. If you can do a threshold analysis, will the threshold improve or not? That is the main question when you do irregular codes. Okay, so, we will stop here, pick up from here next week.